Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In today's video, we're going to be talking about gas laws. And what we're going to do is we're going to talk about Boyle's law, Charles's law, and Avogadro's law in order to form this equation that we call the ideal gas law. So let's get right into it. Okay, so for each of these laws, we're going to try to relate to how it relates to volume. So when we talk about Boyle's law, we're going to talk about how volume relates to pressure. When we talk about Charles' law, we're talking about how volume relates to temperature. And for Avogadro's law, we're going to talk about how volume relates to moles. And as you can see, moles has this variable of N. I don't know why they chose N for moles. I think M would make more sense. My only logic there is that M stands for mass, milli, meters, and there's all these other things that M stands for. So they chose N to represent the moles of a particular substance. Okay, so let's start out with Boyle's law. What do you think the relationship is between volume and pressure? Do you think that's a direct relationship, as one goes up, the other one goes up? Or do you think as one goes up, the other one goes down? Okay, well, I have a nice little, example of Boyle's law, which is this syringe, and I've kind of melted off the bottom, and I placed the plunger right in the middle when I melted it off. Okay, now the pressure in this room is approximately 1 atm, or 760 torr, or 760 millimeters of mercury. Those things all mean the same pressure. And my question to you is, well, what do you think the pressure inside the syringe is right now? Okay, well, it has to equal the pressure that's out here. Okay, otherwise it would move. If the pressure was really high in here and the atmospheric pressure is 1 atm and this was higher than 1 atm, then the plunger would move up. Okay, and the opposite would be true as well. So let's see what happens, okay, when I decrease the volume. Okay, when I take the syringe and I push down, right, okay, I have all those gas molecules in half the space now, okay? So what do you think the pressure is inside the syringe, okay? Well, it's now greater than the atmosphere because when I let go, okay, the syringe returns to its starting position. So let's kind of draw a picture of what's going on right here. So here's my syringe. And in the syringe, there were some gas molecules. I'm going to put, I got 6, 7, I have 8 gas molecules right there. And then I'm going to draw the same exact syringe, okay? But I'm going to decrease the volume in half, okay? And so those 8 molecules, 1, 2, 3, 4, 5, 6, 7, 8, are now a lot closer to each other. So this means that the pressure's increasing as the volume is decreasing. So as the volume goes down, the pressure goes up, okay? And we call that an inverse relationship, okay? So as one goes up, the other one goes down. Now, I want to write a mathematical expression for this as well, okay? And the way I'm going to write that is that P times V is equal to some type of constant, and I'm going to call it constant 1, okay? And just to give you an example, let's say that this constant was equal to 8, which it doesn't, but let's kind of roll with it a little bit. If the pressure was 1, then the volume would have to be 8. If the pressure was 2, the volume would have to be equal to 4 to equal 8. Likewise, if we continue that pattern, so as one goes up, the other one goes down, and as you can see, it goes down proportionally, okay? So this is kind of a good mathematical relationship between pressure and volume. Pressure times volume is equal to a constant, okay? And we've seen this before with like frequency times wavelength equals a constant, okay? And if I wanted to rearrange this equation, like if I wanted the P on the other side, I would write this equation as volume is equal to 1 over P, because it's now a denominator, times that constant, if I wanted to put the P on the other side of the equation. And eventually I want to do that. So here's my equation for the relationship between volume and pressure. As one goes up, the other one has to go down. As I decrease the volume, the pressure increases. So the syringe is a great example of Boyle's law in effect, okay? So whenever we have these flexible containers, okay, that's how we can kind of evaluate volume. And I just wanted to show this one last time. If I was to pull up, okay, on the syringe, okay, now the pressure inside the syringe is less than the atmosphere. And when I let go, the atmosphere is going to push it all on its own to its starting position, okay? So the syringe is a great example of Boyle's law. The next law that we're going to talk about is volume and temperature. How do you think volume and temperature are going to be related? Okay. What I have here is another flexible container. Like if I put a stopper on this, the volume would not change. It would be fixed. Okay. However, I put a balloon on here. Okay. So if it wants more space, the balloon will just kind of expand. So we got this flexible container where the volume can change. And what I'm going to do is I'm going to heat this up, okay, and see what the relationship between the temperature and the volume is. So what is your guess, okay? As the gas molecules get hot in here, what's going to happen to the volume? Is it going to get larger or is it going to get smaller, okay? And I have a hot plate over here, so I'm going to slide the camera over to my lab station. And what I'm going to do is I'm going to put the Erlenmeyer flask on top of the hot plate. And what happens is those gas molecules are going to start getting warmer, okay? And because the pressure inside has to equal the pressure outside because I have this flexible container, you can see that it's starting to take up more space, okay? And the relationship as the temperature goes up, okay, it looks like the volume is going up as well. Okay, so let's kind of bring this back over. We'll let it start to cool down. Okay, go back to the board. Sorry, I'm one-man team here. So it might take a little while for this to cool down, but as these gas molecules cool down, okay, the volume will go down. So let's kind of do a drawing of this on the board, okay, of Charles's law. Okay, so we got this Erlenmeyer flask that has a balloon, and there's our balloon, okay? And then we put the Erlenmeyer flask on a hot plate, and when it heats up, our balloon took up more space, okay? So what we know is that as temperature goes up, the volume went up as well, and we call that a direct relationship. So how do we write an equation for this with a direct relationship? It's simply volume is going to equal to temperature. Well, they're not equal to each other, they're proportional to each other, so we always have to multiply it by a proportionality constant. We're going to call that proportionality constant C2. So if this constant was 8 like I had last time, well, if temperature is 1, that would be 8. Temperature is 2, that would be 16. If temperature was 3, it would be 24. As one goes up, the other one goes up as well. So this is a good equation for volume and temperature with Charles's law. Okay, so kind of running out of a little room there. Okay, the next law we're going to talk about is Avogadro's law. What do you think the relationship is between volume and moles? Okay, well, I have another balloon here, okay, flexible container. There's not a lot of moles of air in here. Well, what do you think is going to happen as I put more moles of air inside the balloon? Well, let's find out. What it looks like to me is as I put moles of air in here, it looks like the volume is getting bigger. Okay. Now remember, the pressure inside the balloon is equal to the pressure outside. Otherwise, it would expand or contract. Okay. Now there's a little bit of air there. It's based on the stretchiness of the balloon, but for what we're doing here, trying to explain Avogadro's law, I think what we're saying is just fine. So let's put some more moles of air into the balloon and see what happens to the volume. As you can see, it's now even bigger. So the relationship between moles and volume, as the moles increase, the volume increases. Okay, so let's draw a picture of this. Okay, so we got here a balloon that's kind of like deflated. Okay, and then as we put in more air, the volume gets bigger. So as the moles increase, the volume increase, and we call that a direct relationship. And it's probably going to look very similar to this one. So volume is going to equal to moles times another proportionality constant. Okay? And this is kind of a great example of Avogadro's law. Just blowing up a balloon is a great example of that. Okay? Now, what we're going to do is we're going to take each of these laws, okay, to form the ideal gas law. So volume is going to be equal to what in terms of pressure? Remember, that was an inverse relationship, so pressure is going to be a denominator. So as this one goes up, this one should go down, okay? That seems to be true according to this equation. What about Charles's law? As temperature goes up, volume goes up, temperature's a numerator. So I'm going to put it up here, okay? Moles is a numerator. So I'm going to put it up here, okay? As each of these go up, the volume will go up. So I think my equation still looks good. And then I have to worry about these proportionality constants. I got C1, C2, and C3. And what we're going to do is we're going to multiply all those together to form a new constant. And we're going to call that constant R. It's going to be called the ideal gas constant. And it has a value of 0.08206, okay? And we're going to talk about those units in a little bit, okay? But what we're going to do first is we're going to rearrange this equation. We're going to do some math and rearrange it, okay? The first thing that we're going to do is we're going to make this volume a fraction. So volume and volume over 1 means the same thing. And then we're going to do some cross multiplication. We're going to multiply these two together. So V times P is going to be equal to TNR times 1, which is just going to be TNR. And then I'm going to rearrange some things a little bit more. The order in which I multiply does not matter. 2 times 3 is the same thing as 3 times 2. So I'm going to flip these. So instead of volume times pressure, I have pressure times volume. No biggie, okay? Same thing over here. I'm not going to call it TNR. I'm going to call it nRT. And the reason we do that is because this is how you're going to see the ideal gas law in all your textbooks. It's always going to be PV equals nRT. Okay, so I just wanted to show you where you're going to find this on your AP equation sheet in case you're taking AP chemistry. Okay, you're going to find PV equals nRT right here at the very top. Okay, and then we got to talk about kind of this ideal gas constant in a little bit more detail. So the first thing that I'm going to do is I'm going to take this ideal gas law, PV equals nRT, and I'm going to solve it for R, okay? So if I'm solving it for R, I got to divide by NT on both sides. So it's going to be PV divided by NT. And the unit that we use for pressure is going to be ATM. The unit that we're going to use for volume is going to be the liter. The unit that we're going to use for moles is moles. And then the unit for temperature is the important part, okay, that we need to talk about. Temperature has to be in the unit of Kelvin because Kelvin is an absolute temperature scale. There's no negative numbers with temperature, and that's the scale that we have to use. You cannot use degrees Celsius or Fahrenheit with the ideal gas law. You have to use Kelvin. And if you forget how to get degrees Celsius into Kelvin, all you have to do is add 273. So if you go up 1 degree Celsius, you're actually going up 1 Kelvin as well. The scales are the same, they're just off by 273. Okay, so this unit here has to be Kelvin. So the units on R are going to be ATM liters over mole times Kelvin for the ideal gas constant, okay? And that proportionality constant is really important for when we solve different problems in the ideal gas law. And I want to do at least one of those in this particular video. The next video series will connect the ideal gas law with stoichiometry. And if you're finding this information useful, please give me a like and subscribe and add a comment. But let's get into the problem where we actually use PV equals nRT. So let me do some erasing on the board. Kind of more smearing there. And let's say I have this container, okay, that has a certain values, okay. So let's say I have this container that has a volume of 2 liters, a temperature equal to 298 Kelvin. And remember, if that was degrees Celsius, we would have to convert it over to Kelvin. And inside, there's 1.20 moles, okay? Well, if I have this information of moles, temperature, and volume, and I'm using PV equals nRT, well, if I have the volume, check, the temperature, check, and the moles, check, and this is a constant that I know the value of, check, then I should be able to calculate the pressure, okay? And that's exactly what we're going to do. So we're going to take PV equals nRT, and we are going to try to figure out the pressure. That is the prompt. What is the pressure? Okay. So I'm going to divide by V on both sides. So pressure is going to be nRT. And since I divided by V on both sides, this is what I have. The moles is going to be equal to 1.20. The R is 0.08206. And remember, that is ATM liters over mole Kelvin times the temperature, which is 298 Kelvin, all over my volume, which is going to be 2 liters. Now, I want to show you the importance of having those units on your R. Moles is a numerator, moles is a denominator. They're going to cancel out because moles is part of the proportionality constant, 0.08206, okay? Same thing over here. Kelvin is a numerator, Kelvin's a denominator. They're going to cancel out, okay? Liters as a numerator, liters as a denominator, they cancel out. So if it wasn't for all of these units on R, we wouldn't get these units to cancel out. So R is very, very important, okay? So if you take 1.20 times 0.08206 times 298 and divide it by 2, okay, you'll get a pressure of, to 3 sig figs, 14.7 ATMs, okay? So this is how we take Boyle's law, Charles's law, and Avogadro's law to form the ideal gas law, and this thing is going to be used a ton in chemistry. And if you have 3 of the 4 variables, you can figure out the 4th, okay? The next video has more of these types of problems, okay, but connecting it with stoichiometry. So once again, if you found this information useful, please smash that like button, okay, hit the subscribe button, and even add a comment. That really helps the YouTube algorithm get this out to other students that might be interested in learning chemistry.